Is this the talk you were expecting? Okay, because it's been on the schedule for like an hour. So you were all refreshing the page. You're not surprised. I found there's a few hours ago they asked me, said that a speaker wasn't able to make it. We have this slot at 3 o'clock. Could you do something? And I'm like, well, this talk is fresh, just recently updated, although it was updated for a virtual talk that I did. So it was set up with like green screen slides and things. So I turned all of those off and turned on more of the in-person style slides. My name's Richard Campbell. I make a bunch of podcasts, .NET Rocks, .NET Radio. Anybody? Oh, a few listeners? Excellent. And super excited to be back in person, back at NDC Oslo. My first NDC was in 2009, which was not in this venue. It was over at the Telenor Arena back in the day. So the only time I have not been in Norway since 2009 was last year. But then nobody was anywhere last year. So, and this show too, which is normally in June, got bumped down to September and got bumped again, and now here we are at the end of November. And I'm reminded why we come to Oslo in June. Now, I'm from Vancouver, where it's plenty dark too, so just not this dark. I mean, it's pretty much over by 4:30, like my. And the temperature I can deal with. I'm Canadian. That's not that big of a deal. I know better to go outside, and I also know the rule that there is no bad weather, only bad clothing. But we were going to talk about artificial intelligence. But this is not artificial intelligence, right? This is James Cameron. This is science fiction, and it's part of the problem of artificial intelligence is that it's steeped in science fiction. And so people's perception of it are kind of messed up. And it's not their fault. We've been messing with them for a long time. The term artificial intelligence is probably older than you think. The first artificial intelligence workshop was held in the 1950s in Dartmouth University. Folks like Marvin Minsky and a few others. And they were, as most scientists are, when they do things that are in public, they were trying to get funding. And they got funding from the US military to build artificial intelligence software to make the military operate more efficiently. It didn't go particularly well. This is pretty primitive computing. This is where ELIZA comes from. So that's like Joseph Weizenbaum, one of the folks that was at those original meetings in the 1950s and the first workshops, developed the first version of ELIZA on a mainframe in the early 1960s based on what's known as Rogerian psychotherapy, which is really where you just repeat the person's statement back to them, because apparently that passed for psychotherapy in the 1960s. But that's the original chatbot, going all the way back to the 60s. And people tend to project intelligence against anything that can chat. Well, people tend to project intelligence onto things in general. It's called anthropomorphism, right? We see faces in trees, or in bowling balls, or mountains on Mars, right? Humans are wired to locate faces, both friendly and unfriendly. You know, you go back to that primitive brain. That primitive brain is looking for the tiger in the forest, right? That face effect is important. It'll keep you alive. And then the fact that we cast behavior onto those faces means that we create intelligence where intelligence doesn't exist. Now, that is important when it comes to artificial intelligence because, again, we're casting that concept onto it. So the term may have first been formed by a set of mathematicians in the 1950s, but regular humans only heard the phrase artificial intelligence when Arthur C. Clarke and Stanley Kubrick teamed up to make 2001: A Space Odyssey in the late 60s. And of course, HAL tried to kill everybody. So we set the tone for artificial intelligence really well. But that's the actual perception of it because we often see that. That's how science fiction portrays it. It's how the term is known and has been known for decades. Now, it's not that Marvin Minsky and Joseph Weizenbaum, those guys, did not succeed in helping the military. The U.S. military's logistical machine is the finest in the world. By the late 60s, they had this organizational system for moving men and materials around in conflict zones that is unrivaled by anyone to this day. But it wasn't artificial intelligence, because the reality of artificial intelligence is that's a term you use for a technology that doesn't work. As soon as it does work, it gets a new name, right? It becomes planning and logistics. In the late 70s, early 80s, as the mini computer and early microcomputers started to mature, we started making expert systems, sort of the next generation of AI technologies. And again, as soon as they worked, we called them expert systems, not artificial intelligence. This is the era of Lisp and Prolog, and really trying to take the knowledge of individuals and program it into heuristic trees. The problem with a heuristic tree, if you get into the mathematics of it, is it hits a level of complexity where it's too complex for any computer of the time, even today's time, to continue to function efficiently. And you end up having to do with tree pruning, different methods for trying to keep that stuff working well. And so by the early 80s, we have these $50,000 to $100,000 mini computers running Lisp that can do a certain level of heuristic training and learning in certain expert systems. And they sell thousands of them, but not much more than that. And things go quiet for a while again. Now, that era of the late 70s, early 80s is also the era of robotics, when car manufacturing and many other repetitive manufacturing processes got automation around them. This is often grouped into the AI bundle, but it is automation, right? We're tech people here. We can tell the difference, that we teach motion sequences to precision stepper motors and don't get in the way of them because you are soft and spread easily with metal arms. But it's one of the reasons that a lot of manufacturing got cheaper, because these things work round the clock. They're very reliable, they're very consistent, and they have changed the way we do a lot of different things. So those are the early stages of AI. Then we get a little more interesting as we get into the late 80s, early 90s. Really what we start to see is a stratification of the culture of the artificial intelligence folks. The colloquial name was the neats versus the scruffies. The neats were the decision tree types, the mathematical, symbolic reasoning approach that said that we could have logical, validatable steps through any given workflow to be able to come up with sophisticated results, largely led by guys like John McCarthy. And then on the scruffy side, it said that real intelligence isn't that organized, that it's more organic and emergent, it's more adaptive, and that we can do this sort of neurological approach where we model neural behavior to get results from data, and it's inconsistent. And so both these schools of thought emerged coming out of the 70s and 80s, and both of them had sort of technological successes going into the 90s. I would argue the ultimate manifestation of the NEATS approach was Deep Blue. So this is 1997. This is IBM coughing up the money for some fairly large computers to do a heuristical learning model around chess, and ultimately is able to beat Kasparov. Just to be clear, when you're talking about this particular computer, which was not the most powerful computer in the world at the time, this is a fairly robust machine in the 1990s, about 11 gigaflops, aka the kind of processing power you'd find in like a Nintendo Switch, but just a few years before. This tech did go on. This is where Watson came from, right? That IBM continued to develop Deep Blue and that heuristical engine into what's become Watson, and Watson has some interesting products around it, but generally heuristic models suffer from the same problem, which is that as the model gets larger and larger and larger, you get an n over n plus 1 problem, where it just gets so complex that it becomes very costly to continue to grow the model any further. So there are certain classes of problem that work very neatly with this neat model, this heuristic model, and then there are models that don't work. And enter the scruffies and neural nets. So starting in the 80s, we started our first implementation ideas around neural nets. Now, these were logical neurons, so they were not actually organized in a nice array like this. They're literally sequentially processed by a computer. But you have a set of input neurons, you have a set of output neurons. The input neurons are some kind of sensor or some data source. The output neurons are the results you're expecting, and then you'd have a hidden layer. and the value connections between these different neurons would ultimately affect the output. What was cool about the neural models, even from the very beginning, was this idea of rather than having a set of inputs, you write a set of rules to get an output, you did training. You had a set of inputs and you had a set of outputs. And you would train the system over and over and over again on sample sets of these inputs and outputs, and it would develop its own rules that you couldn't understand particularly well. But it worked for simple cases, and in the 80s it didn't get very far. One of the leaders of this, and the guy who helped emerge neural nets into the modern world, was a fellow by the name of Geoffrey Hinton, Englishman, teaching in Canada, got his PhD in artificial intelligence in the 70s. And so he wrote, he had gotten to a point with neural nets in the 80s where he said, okay, well, we've hit a point where we don't have enough compute to make a more sophisticated model, but if we did, here's a method for adjusting the neurons in the learning practice so that we called it backpropagation, and it would allow us to be able to train much more sophisticated models, many more neurons, many deeper layers. In these big, deep propagation, what they call adversarial networks, 10 layers deep could be done. But looking at the computers of the 1980s, just was like, it can be done, but it'll take so long, nobody will care. And so it kind of went back on the shelf again until the 2010s. And it was students of Hinton's that were dusting off his old papers and reviewing these models that said, well, we got a lot more compute now. Why don't we try this complex adversarial network approach? But they needed a problem, and they found it in a thing called Imagenet. So Imagenet was an effort starting in the late aughts, 2008, 2009, to build software that could recognize images. A harder problem than we think, right? It's actually really tough to recognize images. And so what the core of this was a collection of 14 million identified images. So they not only had the picture, but they had what was in the picture, what the correct answer was. 14 million images. And so folks for several years have been building heuristic image recognition models. And after a few years, we're getting into the 70% correct range. And it was Hinton's students taking an adversarial network approach, ran through the data, they entered the challenge in 2012, got 85% first try. And the next year got 99%. We all saw this happen, whether you watched this contest or not, because that technology was grabbed and spread around heavily. The biggest space of it initially was voice recognition. So we'd had voice recognition technologies for years. They were just universally bad, right? You would have to speak into a microphone and train your system to respond to your voice poorly. And then one day in 2014, Siri showed up, and it just understood what you said, unless you were Australian, because some accents are harder than others. But really, that's what happened. And the way that it happened was that they took a huge amount of audio in its known statements and fed it through an adversarial network, the same way they did with the images, and got to that 99% result number in something that was relatively computationally efficient. And enough that you would stick it into a smartphone and just make it a thing, to the point where we forget that, here we are 5-6 years later with a miracle. That's how it happened. So we've always had these sort of parallel lines inside of AI, the sort of the neat approach and the scruffy approach, and both have had wins recently. Depends on the class of the problem. And so the best gathering I've ever seen of all of these different technologies is in this graph. A couple of clever things about the graph. The short lines mean the oldest stuff. So you see the planning. Let's see if I can do the little focus zoom thing here. Does that work? Ooh, look at that. Wow. So the planning, scheduling, and optimization, that's from the 1950s. That's the military stuff. In the 70s, we had the expert systems in robotics. Then you have the early speech technologies. And then their longest lines are this latest generation, some of which are heuristic, some of which are neural, all of which are broadening the horizon. And notice all the names that don't say artificial intelligence anymore. Because if there's anything you're going to learn from me in this past hour is that artificial intelligence means it doesn't work yet. As soon as it does, it'll get a new name, and we'll peel that name off and put it somewhere else into something else. And this continues. A group at MIT, the technology called Dactyl. So it's cool that they have a hand that can spin a ball or spin a cube or can roll a coin between its fingers. The cool part is not that it can do it. The cool part is that how they trained it. They modeled this hand in software first. Then they applied a neural net to it using with realistic physics models to learn to handle it before they actually gave it to the robotic hand. So it had 100 years of practice to play with that object before they actually put the object in the hand. That's now what's happening now is we're starting to throw the cloud into the equation and the GPU. Because neural nets fit very nice into scalar computing problems. And if that seems vaguely creepy, well, then you're paying attention. Let's talk about Go. Go is the other win for the Scruffies. So the Neats won chess. It's the Scruffies that won Go. Go is an ancient game, as much as 2,500 years old, depending on who you ask. It's either Chinese, Korean, or Japanese. I'm going to tend towards the Chinese because they outnumber us. 19 by 19 grid, pretty simple game, simple to understand, impossible to master, incredibly complex game. The best players are extraordinary minds. And the DeepMind guys wrote a program called AlphaGo. Took them about 2 years of training, studying games over and over again and outcomes in their various models. By 2016, they were starting to beat world-class players, and in 2017, they beat the best in the world 3-0. Go is beaten. That's interesting. One of the interesting effects of this was that, I think, upset the Chinese government a lot because their AI initiatives really took off at that point. It's like, that's our game, and there are Americans playing it better than us. That's not good. They didn't stop. So Alpha Zero was the next incarnation of this, where they changed the training model. So in the original AlphaGo, they trained against world-class games. So, one of the things that Xi, the guy that the world master that beat, said, he plays sort of like a human, and he gave him he. But not quite. There's something odd about him. It's like, well, it's a piece of software for starters, so okay. But with AlphaZero, they didn't train that way at all. What they did was actually just they gave a model that had the rules and then played itself with the rules and trained for a month against itself, playing as fast as software as fast as it could. And after a month, it was able to clobber AlphaGo. So then they fed it chess, just as a test. And not only was it good at chess, it was better than Stockfish, the now current top-tier chess player. But also, it was more computationally efficient. When neural nets work, they're tough to train. It takes a lot of resources to make. But once it's made, it doesn't take a lot of resources to utilize the model. And so heuristic models tend to have a high overhead in operation, but neural net models don't. What they have is a certain level of uncertainty. Heuristic models are way more consistent. If they're going to lose, they'll lose every time. If they're going to win, they'll probably win every time. Neural nets are a little bit odder than that. Now, this is cool, but it's also chess and Go. Can we make this matter? So this is the most recent research, same technology stack, but now they've applied it to something more important, protein folding. So protein folding is an incredibly complex piece of biology. There are only a few hundred distinct proteins that we know of in biology, but when you interconnect them, they fold in unusual ways that change their behavior and characteristics. The current estimate for the total number of protein combinations known in Earth-based chemistry is 10 to the 300th possible combinations. So don't try and run them all. So smartly, as we've been learning more about protein folding, we've created a competition called the CASP competition, where we have several hundred known protein folding patterns. And so we're trying to build software that can predict, based on a set of proteins in a connection pattern, what the fold construct will be and what the basic behavior will be. These have been going on since the 90s, but in the last couple of years, we've gotten to a point where literally this year, AlphaFold 2 scored in the high 90% of recognizing these known protein folds. if we're right, if this is actually working, this changes the way we approach chemistry and approach medicine. Like, there's a lot that can be done here. It's almost hard to conceive of. The paper I've read so far on this, because it's literally been in the past few months that we've gotten these results, nobody believes it. Even though the numbers are working, it's clearly beaten the test. It's like, okay, is it beating the test, or does it actually know how to fold proteins? So now the bet is on to take one of the protein folding solutions that AlphaFold 2 is solved and solve it another way that isn't already known, to see if it's actually shown us a new folding result that we don't understand yet. That to me is pretty exciting. But if you get a sense that this is a little voodoo-ish, you're not wrong. You know, one of the side effects of us taking inputs with a set of outputs and saying, now you figure it out, is it doesn't come back and tell us how it figured it out. So we're getting results, but we don't necessarily understand how we're getting the results or why we're getting the results. None of this looks like Terminator so far. And the conversation around artificial intelligence always gets to that. You know, are we going to make a mind? Right? Everything I've talked about so far has been an artificial specialized intelligence. It's specialized in Go, or it's specialized in protein folding, specialized in image recognition, all known sort of behaviors, specialized things. What about a generalized intelligence? And if you think back to a few years, as gains first really took off and these new neural net models went big, which 2012, 2013, 2014, we had a lot of popular tech folks, guys like Elon and the late, great Stephen Hawking, and even Bill, very concerned, implying this idea that we're going to build an intelligence that will destroy the world. It was never true. What they were really concerned about was that the technology that had been grabbed from the various laboratories like Hinton's and was now being developed en masse was largely controlled by a few big tech companies like Google and Facebook. And really the pressure was being put on to do this work in the open. Right? We don't want this stuff done secretly in a way that we could have nefarious results, right? You saw Microsoft with Tay trying to learn language interaction in a meaningful way, and be quickly turned into a racist monster until eventually they just turned it off and said, sorry. And ultimately that pressure succeeded in creating OpenAI, which is a collective of all of these major players in the AI space to kind of do AI in the open, to share code and show how results are being built, try and make a relatively trustworthy system. Seemed like a good idea until GPT-3. And this is also recent news, right? So GPT stands for Generative Pre-trained Transformer. What we really know is this is the best language engine we've made so far. At least in English, it's remarkably good at understanding what you're saying, taking things in context, and creating excellent responses. And so as GPT-3 emerged from the lab as part of OpenAI, they were expected to make it open source. And there was pushback both inside and outside of OpenAI. The concern being, this thing writes so well that if you wanted something to manufacture fake news at high velocity, here's your tool. Like, it's killer at it. And so ultimately decided not to release the source code. Anybody can use the GPT-3 engine. It is available through OpenAI. You just can't have the code to run on your own. You have to run it through them. So they're now acting as a gatekeeper, with ostensibly the goal to limit the negative behavior that could be used with this technology. And that's the concern we have. The peril part of this rapid evolution of these new technologies for us is, what will we do with them? Image recognition is incredibly useful, but it can be super creepy. A few years ago, Microsoft did we'll call it an aspirational demo, because it's never been seen again. And you may have seen this, it was streamed, and the video's out there, of a construction site with cameras all over it. And there is an artificial specialized intelligence watching everything moving on the site, being able to identify all people, most tools, and hazardous situations. In this particular scene, it's acknowledging that the hot saw, which is a fairly dangerous tool, has been put away inappropriately. And because it can recognize the person in the shot, it essentially rings that person's cell phone to say, put the hot saw away, which is creepy. There's this concept called the uncanny valley. It's really typically applied to humanoid robots. This idea that wired in our back brain is we're looking for faces until those faces are the wrong kind of humanness, and then they're really gross and they're repulsive. And so when the Disneys of the world and were making animatronic robots and things, they would deliberately make them cartoony so that they didn't dip into that uncanny part. But I'm seeing uncanny valley emerge from all sorts of AI technologies. That reaction you had to my description around the construction site, everything was fine with that until the software phoned the person to tell them what to do. Then it wasn't fine anymore. And I think we're dancing with this problem of dipping into the uncanny valley. What's the right way for us to use that safety feature? What happens if we count how many times you go to the bathroom or take a smoke break or how long you spent on lunch? Because that's easy to do with the current generation of image recognition. Right? And you ask the Chinese government how effective their image recognition systems are today and their ability to create a citizen score based on your behavior in public anywhere in any major Chinese city. We're at this turning point now. We have this tool. What are we going to do with it? Now, not the first time we've been in this situation. You back up to the end of World War II and the nuclear bomb. We made a thing. Arguably, we made it for the wrong reasons. We thought the other guy was making it, so we needed to make it first and spent an astronomical amount of money to prove a fairly tricky scientific concept that turned into one of the most destructive weapons ever. And we could have a long conversation about the good and bad of nuclear weapons because we haven't had an all-out war since. It actually scared us straight. The reality was that the scientists that were behind it, guys like Enrico Fermi, he's the Trinity guy who built the original bomb and the one who said, I have become death. And the other fellow there is Edward Teller, who made the hydrogen bomb, because the only thing better than a big bang is a really big bang. But the more important part was that the inventors stayed involved. They were part of the control system around nuclear weapons. And the AI technologies we've got today are starting to move into that class. And suddenly it's up to us. It's our responsibility. If you want to make 1984, and I was trying to find a 1984 cover, and it turns out there's really a lot of 1984 covers. Like, it should be a hint when a book has this many covers that this dystopian concept of a world needs to be facilitated by technology. And when I look at this last cover on top, this war is peace, freedom is slavery, ignorance is strength, boy, that Orwell's pretty clever. He just missed by a couple of decades. We're living in a time steeped in creative lies, in ability to manipulate masses through various means. And AI technology is playing part of it. This is actually a few years old now, but let's see if it actually plays. How are you doing? You going to come up for me? Have you seen this before? This is sort of the original deep fake demo, right? This is University of Washington technology. And it's not actually Obama. What they've done is taken video of Obama, fed it through a GAIN network, and then added in a voice actor. And here he is right here. Now, this was the best back a couple of years ago. Then there was this one from Belgium. And it's terrible, right? It's a protest video actually focused on the fact that Belgium's not following the Paris Accords, and so they made up a Trump one. The problem is everybody believed it. It didn't matter if you made a good version, bad version worked just fine. So what do we do when we can't understand the video anymore, right? We can't trust we can make any of these things. The organizations that are involved are trying. So we have this partnership on AI. These are all the big players. For the most part, these advanced AI models depend on the cloud. So the cloud owners are going to become gatekeepers. For better or worse, I don't know if they're the good guys or not. And I've worked pretty closely with most of them. Like, they're generally pretty good people, but large American corporations have their problems. And so, you know, when I look at that line, it's like, you know how these folks are. Are these our gatekeepers? I mean, the alternative is it's run anywhere, you know, and I think about GPT-3 for this. It's an interesting challenge. We haven't even dealt with the data quality problems, right? That FATE, this fairness and accountability practice, is really recognizing that most of the data that we're feeding into these systems comes with significant biases. Let's not say most, let's say all data is. It's not a bad thing unless you don't acknowledge it and deal with the fact that those biases are going to be amplified by software, as is usual. You know, to err is human, to really screw up takes a computer. You know, one person will mess up an invoice, but only software will mess up 100,000 invoices. And so if you take a seriously biased set of data and you feed it into a machine to help make decisions for you, you're going to amplify that bias, whatever that may be. We also got the problem with the explainability piece. So DARPA, for a while now, has had this initiative around explainable AIs. This is specifically the neural net problem that says, can we break neural net results down into individual steps that will help us recognize when it's correct and incorrect? Because as long as the AI model is correct, nobody cares. It's all fine if it gets the results right. It's when it gets results wrong. I had to go back and watch the iRobot movie again. I mean, it's not Will Smith's best work, but the whole point of the movie, that inflection point, was the software, the robot, made a decision the human wasn't comfortable with. That Will Smith's character got saved and not the little girl. We're going to use some kind of artificial intelligence model to drive cars. We're trying now, somewhat unwisely, folks would say. And all of this is fine until the software makes a decision that a person wouldn't make. And then we ask the question, why? And the fact that we, at this moment, could not tell you is pretty disturbing. We're the software people. We're supposed to know why the machine did what it did. Now, I admit it. I mean, I've been doing this stuff for a long time, and I'm often not sure what the machine's doing. Sometimes the computer even tells me to check with my administrator. And I'm like, hey, I'm the administrator, and I do not have a clue. And that wasn't even doing artificial intelligence. But this is what we're facing, is we're building software now that we cannot explain to ourselves. The data that it's generating that creates the behaviors that we want isn't clear to us. And that should be unacceptable. There's no litigation or legislation around this yet. This software is out in the wild. As long as it's identifying cats, it's fine. As long as it's getting, doing some facial recognition, maybe fine, until you do something inappropriate with facial recognition. You may have seen the Taylor Swift issue a few years ago. Do you know this story? Talk about an interesting facial recognition problem. So Taylor Swift has the largest number of registered stalkers in the world, a little over 3,000 that have restraining orders. They're not allowed to be within 100 yards of Tay-Tay. And on average, 2 of them show up to every conference. If only we could find out which 2, things would be good. Can you imagine how hard it is for security for Taylor Swift, knowing there's 3,000 different people that have to be kept away from her? You can't memorize all those faces. Which 2 are here today? And so they paid a company to build out a system that goes into the stadiums that is a digital signage system. So, which points you to the way to the T-shirts and the bathrooms and so forth, but it's also got cameras on it because everybody looks at signs. They get good pictures of everybody's face. And before the concert even started, they've identified which of the people that are on the list are in the building. They send those pictures to the security folks so they can find them and take them out. the same time, they have a picture of absolutely everybody's face. Now, that's not necessarily a crime. We have lived in a surveillance system for decades. It's always a question of, what did you do with the data? All right? I'm all for protecting Ms. Swift, just as long as you delete the data at the end of the day, right? And I think about a couple of the concert incidences that have happened recently. I'd kind of like to have detailed video footage of everything to see how did we get into a situation where people were trampled or crushed, and how did the responses happen. I think that data is useful as long as it's handled properly, that people's privacy is protected. It's only used for appropriate circumstances. This is a legislation problem, that we actually have to insist that our non-technical legislators can write good legislation around this. You know, hey, here we are in Schengen, at least, and approximate to the EU, and we have the GDPR. Not perfect, but an attempt, something we could deal with. I mean, I certainly need to tell more people about my cookie status. But we get back to, we can legislate around this. We can't just ignore the technology and hope it'll go away. We have to set rules. The correct answer is not go backward. I understand that the city of San Francisco has banned facial recognition software inside of the city. I don't think it stopped it. And I also think it was correct practice. I think you have to register. We have to have the rule set of how you handle that data. And we should be able to use it for good and try not to use it for evil. Let's deal with another aspect, and you're going to probably be confronted with this, which is AI going to take all the jobs? And my answer is no. Automation's doing that just fine. We don't need artificial to take jobs. Goodness knows, we're in the software business. We know how to take jobs all day. And it was the Luddites, back in the 1800s that were weavers. We've heard the term Luddite. What was going on? 200 years ago, weaving in England was a big business, right? Making cloth. And the first generation of automated looms, the Jacquard looms, was coming into play. And they used steam engines, largely developed in the UK, with this French automation equipment to weave cloth much faster. And the manual weavers were scared of it, and they attacked it with axes. It didn't end there, oddly enough. They rebuilt, and they retrained most of those manual weavers to operate the equipment and made far more cloth. And the byproduct of the automation of cloth weaving was that it lowered the price of cloth a lot, so that far more people could afford it. And the clothing industry in England exploded. Automation is disruptive, but it tends to increase utility of product. You make more product for less money. And so actually, more people were ultimately employed in the automated production of clothing because the demand of clothing grew dramatically. Now, this is not an uncommon theme. When the internet took a hold with the general public, travel websites became a huge thing, and travel agents were massively threatened. Most of them got out of the business. Not all of them. There were always specialty travel agents that worked certain aspects. If you were really good in this space and you wanted to stay in it, you could. But an awful lot of travel was now booked directly through websites. The consequence of that was a tremendous growth in travel, to the point where far more people are employed in the travel industry than ever lost jobs in travel agents. And the demand of travel agents has ultimately grown for more and more sophisticated travel as average people have traveled, to the point where there are more people employed by travel agents today than there were before the internet got involved. Same pattern. Automation expands markets during its disruption. The challenge is taking care of the individuals that get disrupted, because the opportunity space is inevitably bigger. The grocery store checkout line is a fairly primitive process. Now, the original grocer, if you go back to before the supermarket, was someone who stood behind a counter and you walked up to them with a list. And they took your list and went into the back and grabbed your goods for you and brought it all out, and you signed off and off you went. The supermarket was the technological improvement of that allowed you to walk around the grocery store and collect your own stuff, right? But it also created all kinds of new marketing problems because now you are trying to assess the quality of the onion or the quality of the potato, and you're not qualified. Your old grocer was, but if your old grocer would also say, hey, I know you're going to make soup with these onions, so I know they're not particularly pretty, but I'll give you 20% off of them, and they'll make good soup. So they actually utilize product better, which today, once the product looks a little gross on the counter, nobody buys it, and it gets thrown away. Right? Byproduct of our modern system. And we have this new checkout system. Well, it was new at one time, 40, 50 years ago, where you had a clerk that would enter the prices of all the things to complete the total sale. Now, we could automate this. Anybody ever seen a Baxter robot? Industrial robots are good to observe from afar because they really don't care about humans, and they will smash us to bits. That's why they tend to be in cages. But a Baxter's not like that. A Baxter's about $20,000 in the base configuration, and it actually has a good sensor rate. It'll lean away from you if you get too close to it, which is also a little creepy. And what Baxter's doing here is not working a grocery store line. Baxter's doing something weirder and even more disturbing, which is he's actually boxing up another Baxter. But we could do a drop-in replacement. Baxter actually makes a pretty good cappuccino, too. So if you wanted to automate operating a coffee machine, you could do it with a Baxter. But that's not the direction we've gone in at all. We have gone to self-checkout, which sucks, right? It was hard enough to just pick your own groceries, but you decided you'd fake your way through that. Now you got to figure out how to scan PLU codes and UPCs. That's better. And then Amazon came along with their Amazon Go stores, where everything's tagged with an RFID tag, including you. So you've already signed up your account. As soon as you walk in, it recognizes your credit card's entered, so you're in there. You pick up the things you want, and when you walk out, it charges your card. There's automation, right? It reduces the friction of sale. This is a real thing. That store's in Seattle. There's a couple more, and they now own Whole Foods. So if you would like to be automatically charged a ridiculous amount for food, they could automate Whole Foods for you. This is not necessarily artificial intelligence. This is automation being applied over and over again. And the fear around artificial intelligence eliminating jobs is really the fear of automation and the fact that artificial intelligence expands the range of potential automation to much larger scope of roles. And automated driving is a huge part of that. The main piece of automated driving that will make the largest difference to society will be long-haul trucking. True in North America, true in continental Europe. And certainly right now we have a crisis in drivers. It's like, boy, automated trucking, not a bad idea. We'll probably do this for long haul first for a few reasons. One is that's the most difficult job in the sense that you're away from home a lot. Like it's a bad job, even though it pays quite well. But more importantly, truckers are strictly regulated. You're not allowed to drive more than 8 hours a day. Then you have to rest for at least 10 hours, and you can drive another 8. If you can drive up to 11 on the last day, but then you cannot drive for 24. But if you're only using a truck every 8 hours a day, that means it's parked 16 hours a day. If you can automate that part, you triple the utilization of the truck. That's amazing. That's a huge impact. So imagine if we just did the long haul part. At the outskirts of major cities, we have these trailer parks. The automated vehicle comes in, drops the trailer, maybe picks a different trailer up, goes back out on the highway, only drives on the highway. The human drivers then take from the yard into the cities, more precise, more difficult driving, but they also get to go home at night, so it's a better job all around. When you look at produce, just produce, your typical head of lettuce, which depending on where you live, I mean, in Vancouver, it's 75 cents for a head of lettuce. We are in Norway, so what? $2? I don't know. More than half of the price of a head of lettuce is its transport. That's the reality because it's a very low-cost thing to produce, but it has to be transported in a chilled space in a relatively short amount of time. So the byproduct of automated trucking of produce is a drop of 20 to 30% for most produce. More of it in less time for less money. That's increasing the quality of food availability for everyone. Like, that's the real byproduct of this. Now, in North America, Long-haul trucking represents somewhere in the neighborhood of 7 million jobs. And with the recognizing the automation increases the productivity of the long-haul truck by 3 times, you are not going to drive manual trucks for very long the moment the automated truck works. That changeover is going to happen fast because you'll either change over or be out of business. There won't be any choice. But again, you can already see that automation effect. The byproduct of the super efficient transport is a decrease in the cost of transport. That is a rapid shift. It makes more things available for less money. There are more details to this. It gets harder, right? Now, if we get into smaller vehicles and driving in small spaces, we've got to make sure that A is right. We better have explainable neural nets by then, because you really want to know when an automated car makes the wrong choice, what's going on in there. But we might be able to make the long haul thing work first. But the story for this each time has been, ultimately, these are tools. They're very powerful tools. They're tools that can be misused, but they are only tools. And so they don't have an ability to do anything without us as agents. It's up to us and how we use them that makes a difference. But their potential is tremendous, just like every other great tool we've built along from fire on up. It's just a question of using them well. You'll notice I didn't really spend a lot of time on the generalized intelligence because we don't know how to build it, and we're not even really working on it. Because for what? We tend to apply a heuristical model to a given effort in any piece of technology that we build. It's for this, right? We're not real good at the whole it's for everything, right? You always define a problem space each time you start working with a tool. Well, that is not how a human mind works. A human mind works on a much broader spaces. It can derive its own questions in its own problem spaces. That's a very different kind of problem. One not particularly suited to a tool. So it's science fiction, right? There's this belief that if we put enough of this stuff together, an intelligence will emerge. Except that everything that's ever happened in science and physics shows very clearly the opposite happens. You put a big pile of stuff together, it becomes a mess, right? There's not an emergent coherency to something. It's entropy. It becomes less coherent. So don't worry about intelligence emerging out of nowhere. You want to be afraid of something? Be afraid of the technology we've already made being used inappropriately, because that's happening in different parts of the world. That's an actual issue we could address today. And you're going to be faced with this. As these tech tools become easier to use, more available in more places, we're going to have to make choices on how we use them. It'll be up to us. We're the Edward Tellers now. What were you going to do with our bomb? It's up to us. We have lots of choice. And it's a great time. You know, goodness knows we wouldn't want to be bored. We're going to work with these technologies. They aren't going to go away, and we'll do great things. I hope you had a great conference. We've got 2 more days to go. Pace yourself. It's a lot, and it's been a while since we've been in person. Thank you for your time.